the field to the other side of the field fully autonomously, we would need a lot more feedback than most typical robots have, right? So we would want to have some kind of algorithm where we could do slams, right? So we can simultaneous localization and mapping. We want to have absolute reference coordinates of where our robot is on the field, right? So with the normal path following that we do for autonomous, because it's the first 15 seconds of the match, we can use the encoders and the gyro to build odometry, right? And it's accurate enough. It's pretty accurate. We can apply some kinds of filters to it to make the mapping a little bit more accurate and our localization more accurate. But by the time we're, I don't know, 100 seconds into the match and we now want to perform this path in teleop, we don't really trust our localization data from the encoders and the gyro anymore, just because there's a lot of built-up error that could be in there. So if you were to use an algorithm like SLAM, where you had an absolute localization method, maybe running from a camera or a LiDAR, that would be that would give you a much more absolute frame of reference. So let's say we have the SLAM set up, and we know exactly where we are on the other side of the field, and we know where we want to get. Okay, now we have obstacles between us and the other side of the field, right? So now we'd want to look into doing some kind of collision avoidance, where if you sense an obstacle in your path, we have to regenerate a new path around the obstacle to get out of the way, right? And there are a lot of different ways that you can do that. You can use the SLAM data correlated with a bunch of other stuff, and then you can come up with some new kind of path generating algorithm to get your path out of the way. And then, once you get to the gear, even with all of this stuff, to kind of like finalize, once you get to the peg, right? Even with all of this other stuff that we're doing, to finalize our actual position to place the gear onto the peg accurately, you'd still probably want to use vision to align yourself using the tape right there, right? So that's only in the scenario of you cross the entire field to get there in teleop autonomously, and now you want to place the gear. If you were in autonomous mode, within the first 15 seconds, you should easily be accurate enough that using just encoders and a gyro, you don't even need vision. You can just place the gear on the peg like the Cheesy Boost did, right? So I think that a scenario like that, where you want to cross the field using path following, you're really now approaching things like autonomous car driving full algorithms. Like you would want the computer from the Tesla on your robot instead of the RoboRio. There's just a lot of stuff that you need to keep track of. And it would be awesome if we could do that. And it's not to say that we can't, right? NVIDIA has the Jetson board that you can run ROS on that and do a lot of like SLAM algorithms and stuff and correlate that data. I just feel like that was a project that you probably want to be working on for 2 or 3 years before it would kind of make it to the field. So I just think it's difficult. It's almost impossible. And I shouldn't say that it's impossible.
But in your experience, people don't actually try to tackle that problem.
Right. What you could do is generate small paths, right, to do driver assistance actions. So one thing that we did in 2017 was, after our drivers placed the gear onto the peg, the robot the spring would go into our robot, trip a sensor, and then the robot would take over autonomous control, right? So then it would place the gear on the peg, and it would automatically back up away from the peg, and then the drivers could resume control after that. So for short instances like that, you could use path following in teleop, right? If you wanted to maybe have your robot drive out in like a nice S-turn or something to get out of the way and back, so that way now your drivers are facing the rest of the field and you're away from the airship. That's kind of a more realistic scenario, shorter trajectories that you can do based on relative assignment. Like, it doesn't matter where you are or where you end up. You're just trying to perform an action as accurately as possible. It also depends on what path following algorithm that you want to use, right? So there's a few different options. And we're going to talk about that a little bit towards the end if we get to it. So hopefully that kind of answered your question a little bit. You're welcome. Very welcome. Okay, so periodically throughout the presentation, I'm going to be checking my phone. Not because I'm checking my phone, my notes are on here. So I don't want you guys to think that I'm just mean. So first, I want to start today with, actually, I don't even know if there's chalk here.
There is, it's in the box.
It's in the box, okay. Oh, look, there's a whole box of junk. So I want to start today talking about what are motors and encoders, right? So motors, everyone knows they're just devices that we can apply electrical current to and use them to move our subsystem, right? But do we really know how those things work inside, right? Do we know how the current affects the output of the motor, torque, and those kinds of things? So I want to look at that. I want to look at what do encoders do, right? Like how many of you guys know what encoders are? Oh, everyone. That's pretty much everyone here. That's good. Okay, so maybe we can skip through the basics a little bit and get right to the good stuff, right? So how many of you guys are familiar with good system design, like using motor curves in order to design your subsystems and gearboxes to best accommodate the motor's attributes? Few people? Okay, so we'll talk about that. Okay, so I'm going to try and gear the presentation towards what you guys want to learn, especially since there is another presentation that I covered all the basics last week that will be released soon. So feel free to interrupt anytime you want to ask questions. Don't feel like you're stopping me from talking about anything. Anytime you have a question, feel free to raise your hand. You don't have to wait for me to ask. Go for it. So encoders are just devices that track the number of rotations of our shaft, right? From this, we can determine the velocity of the shaft, and that allows us to do all kinds of cool things. One important thing, like a design note that I would say with you designing with encoders, is that you always want to make sure you put the encoder on your output shaft of the subsystem. And there are a lot of people that argue about that and say, well, it doesn't really matter if you put it on the output shaft of the subsystem because you can just do math on the gear ratio to determine the number of encoder ticks required for this and this. But it's just not something that I would recommend doing, because if your encoder is not on the output shaft of the transmission, you can't use it to accommodate for certain things. Like sometimes we want to remove gear latch from a system. It helps if the encoder is on the output shaft. It's easier to track the velocity of systems if you have transmissions that do any kind of shifting or anything like that. You're really just better off putting it on the output shaft of the transmission. Some people will argue that having it there will reduce the accuracy of the encoder because you don't have the scaling is just 1-to-1 on the output. But with encoders nowadays, they're so accurate that it almost doesn't even matter, right? Like the accuracy that you would have having it inside of a transmission between gear stages, it's almost false accuracy because it's just not important. Question?
Yeah. What about like the magnetic encoder?
Perfect. So the only encoder that I actually recommend using is the Cross-the-Road Electronics magnetic encoder. Right? There are other encoders available. They have the light disc encoders that I think come in the kit of parts. Those are awful. They're very difficult to align, and they're very prone to dust. I think US Digital makes a sealed shaft encoder that is less prone to dust, but I still don't really like it. If it's issues with encoders that are on shafts like that, there's gray hills as well. But if you have any kind of vibration in your subsystem, it'll just eat the insides of the encoder, right? So Gray Hills, they make a ball bearing encoder, which is much more durable than their other encoders. Still prone to vibration, right? Even with the best ball bearings, if you have a system that's not balanced and it's spinning, it's going to eat the encoder. So with a magnetic encoder, it's fully contactless, right? There's nothing contacting the encoder from the shaft, and the shaft just spins. The encoder is happy, everything's happy. It's got a little indicator on it to indicate alignment so that it's aligned correctly to the subsystem. It'll just, if it's good, it's green, it tells you you're good to go. Done. There are other encoders available that are magnetic encoders, like the new AndyMark Redline encoder kit that they make. The encoder itself is good, but I have heard some issues with connecting it to the motor controllers as far as the pulses that it reads. There's like a scaling issue. I'm not sure if they fixed it yet, but I just don't see any reason not to use the cross-the-road electronics magnetic encoder. If you're putting the encoder on the output shaft like we talked about, and you're using the Talon SRX, which is really the only motor controller that I would recommend using, there's just no reason not to use that magnetic encoder. One benefit of the AndyMark encoder is that I think it can track up to 22,000 RPMs, and the crossover electronics encoder can only read 15,000. If you have an output shaft spinning more than 15,000 RPMs, you probably want to rethink your subsystem design, right? So just don't do that. So one of the things I said was that I wouldn't recommend using any motor controller other than Talon SRX. Does anyone have any idea why that is? Yes?
The Talons are a lot more, like you can do a lot more with them to store data. They have slots for the encoders with slots. They can be easy to chain together, so you don't have to deal with the annoying PWM stuff.
Right. Right. They have CAN bus, which is a huge benefit for us. What are some reasons why teams don't use the Talon SRX? They're expensive, right? And I'm here to tell you, save money on other things, right? Don't try and save money on your motor controllers. If you want to do motor control, I don't care if it's for a drivetrain, if it's for an intake wheel, if it's for anything, just do it with a Talon SRX. They have a motor controller called the Victor SPX, which is supposed to have all of the same features almost as the Talon SRX, but we tried using the Victor SPX for slave Talons, right? For, you can set up the motor controller so that you have a follower for a master, right? You have a master and a follower mode. And we tried using the Victor SPX for that, and it turns out the Victor SPX does not have onboard current sensing. So we tried to do some monitoring of our subsystems to determine if all of our motors were operating effectively. And then we have like a diagnostic mode that we run that'll compare all of the motor currents within a subsystem and determine if there's anything out of spec. So we tried to do it, and the current kept coming back as 0. So I emailed the company, and they're like, oh, yeah, well, if you read the data sheet, you would say right here, there's no current sensing built in. I'm like, well, this is no good to us. So just use the Talon SRX. The cost savings for other motor controllers just isn't worth it. I think that if you're savvy, you can find other places to save money. And when you get a Talon SRX, you have all the features available that you need. Okay, that rant's over now. Are there any questions about that so far? Okay. With the Talon SRX, we have control mode built into the Talon that we can use to control our motors, right? So we have onboard PID, which is one of the motion control algorithms we're going to talk about today. We have onboard motion profiling, which is like fantastic for all these different kinds of subsystems that we want to control. And we're going to talk today that that's really the only control mode you should be using for the majority of your subsystems. Positional control subsystems. Now, Talons have the CAN bus, right? And there are a couple design caveats when designing things with CAN bus. The CAN bus on the Talon must be connected correctly on each end of the system, right? So we're going to have our system here. It's like our Robo Rio, right? We have our little CAN bus port right here. And then we have the power distribution panel. And there's a CAN bus port here. So within a CAN bus system, there is a network, right? It is a computer network. Now, every Talon has 2 twisted green and yellow wires leaving the Talon, right? Now, these are the network wires. They're the CAN bus network wires. There's a CAN high, CAN low. Every pair, right, is passively connected inside the Talon. So even though the wires leave the Talon, they're distinctively 2 separate pairs. Inside, they're passively connected. So the way CAN bus works is that there's a passive connection between both green wires and a passive connection between both yellow wires. So within the entire bus, all of the devices are literally just connected together. And that has a few different implications for things like bus bandwidth availability and frame timing from the motor controllers. So when we want to do onboard control on the Talon, we're gaining a few benefits that we don't necessarily have from other types of control. And I'll get into that a little bit more later. With PWM is different because the PWM is connected directly to the Rio. So whenever you send an update, it's whatever loop rate you're running the PWM at on the Rio. Now with CAN bus, if you send updates over the CAN bus, there are buffers inside the Phoenix library inside the Rio, and there are certain times when frames are sent and times when they're not sent, right? There's transmit times so that the CAN bus can still have a stable utilization percentage. So if you try to do too many things, your CAN bus utilization percentage can spike up to like over 90, 100%, whatever, and then your devices will start missing frames, stop receiving everything, and then they'll pause, they'll jitter, they'll have all kinds of weird problems. It can be caused by you're trying to do too much stuff at once. So let's look for a second at the physical connection of the CAN bus, right? So we have our devices here. And the squiggly line means twisted pair. So at the end of the CAN bus network, on either end, the Bosch spec says we need a 120 ohm resistor. Right? So we have that, and we have one here too. They go. What's that?
You're saying that's built in.
So interestingly, yes, in the Rio, the 120 ohm resistor is built in. In the PDP, right, this is the power distribution panel. In the PDP, there's a jumper that says, like, do you want this terminated, yes or no? Just say yes, right? Always have this resistor in circuit. You have the option of adding your own CAN terminator resistor if you don't want to use this, but you shouldn't. Like, it's built in, it's here for you. Why would you just choose not to do that? Just make sure that the jumper is enabled, because I have seen a few where they're not, and I'm not sure why that is. I don't know if kids are just like playing with them and they're like, "Ooh, this looks fun," and they're sticking it in the wrong place on and off, or if sometimes they come that way from the factory. I don't know, but it's something you should check. Okay, so the CAN bus spec says that we should have our networks designed as such, right, with a terminator on this end and a terminator on this end, the 120 ohm resistor being the terminator, and then our network devices in between. Now, for some system designs, it's okay to have a branch node, right? So we have like another Talon out here. And then we have our second wire. This wire just doesn't get connected to anything. There's no terminator that goes on the second output here on the branch, right? We only have the ones on the ends of our main network. We don't want to put another terminator here. But within this network design, you shouldn't really ever have more than one branch node, right? Like, you can have multiple devices connected here, but you wouldn't want to have branch all over the place like that. That would be the wrong design. CAN bus, yes.
Just like physically, how would you connect that
To a twisted, well, you'd untwist it and then
just
cut it. And so the way it would look is, right, we have a green wire here, and then you'd have the green that would go along this way, and then you would splice in your green wire here. Then you'd have your yellow wire going along, and then you'd splice in your yellow wire here, right? And then these two wires would be your branch node that comes off of that. With the CAN bus, it's pretty resilient to things like electrical noise and errors. Because of the twisting, there's a lot of noise cancellation that you gain from having a twisted pair of wires like that. The protocol itself is a differentially signaled protocol, meaning that the signals in the green and the yellow wire are exactly opposite each other, right? So if you have a digital signal, how many of you guys are familiar with seeing a digital signal that looks like this? Okay, most of the people. So basically, this would be a data transmission, right? This would be an electrical signal. We could have either 0 or 1 in digital logic, right? So if it's low here, we would consider this low. This would be a 0. This would be a 1, right? On a normal electrical signal. Now with CAN bus, because we have a differentially signaled bus, we're going to have a second signal that's the exact opposite of our first signal. Right? And then the data that is transmitted is actually the difference between the two wires. Right? And then this would actually be a 0, I believe. And then this would actually be a 1. Right? So this is good for a few reasons, right? It's more resistant to noise because if our electrical characteristics on either signal are just a little bit off, because it's differentially signaled, hopefully both of our signals are off by the same noise amount, so our difference is the same. That will help lessen certain things. Errors of reading bits and things like that. And in addition to that, it's good. We don't want to get into it too much. I could talk for days about CAN bus, but we're not going to. So one thing that it is not good at is dealing with a broken wire, right? So like if this wire was just broken, your whole CAN bus is down. Like everything is toast. If this wire is broken on our branch node, only these devices are down, right? And that might be something like an enticing thing, like, oh, well, I should just build everything with branch nodes, right? Every device has its own branch. That way, if anything gets cut, everything's still up except that one thing. That is not true. Don't do it. That's bad, right? When everything is on a branch line, that's not how the network is supposed to function. There are implications about that that could cause you issues further down the road. You shouldn't do that. You should just make sure that your wiring is good. And it's not going to get cut, right? Put it in like protective sheathing or something. Just make it nice, tied down, not flopping around where somebody else's battle box can just chop it, right? Make it all nice and neat. So I think that with CAN bus, because we talked about having all of the devices are actually passively connected together at once, and we now said that our data transmission looks like this, that means that every device needs to apply an electrical signal to the same two wires at the same time to send data back and forth everywhere, right? So they have a built-in way to do that and determine if there are any other devices communicating on the bus at once, right? And then when another device isn't communicating, then this device can begin its communication. So what happens when we use too much of the CAN bus bandwidth, there's not enough downtime in the signals where a signal isn't being applied that the device can actually send its transmission. So then you don't get data, then things start to not work. So one way to approach this is to actually manipulate the CAN bus frames inside the Talon, right? The Talons have built-in programming that they have status frames, right? And these status frames tell us a lot about the Talon. They sometimes are actually used to control other Talons. And understanding how the status frames work can really help you optimize the CAN bus bandwidth that you're using. So on the Talon, there's things known as the general status frame and the feedback frame. Those are the two that we're going to look at today. And also the control frame, right? The control frame is not a status frame. The control frame is actually a frame that we're sending to the Talon to tell it what to do. So when we're using Talons in follower-slave mode, we don't really care about the data that's coming from them, right? We don't really care about the output value that Talon is being put out, because it's just copying the value from the master. We don't really care about the feedback value from that Talon because we don't have a sensor connected to it. So we can take those frames and slow them down. The default transmission time, I think, for the general and feedback status frames is like, it's 20 milliseconds, I think. It's 10 or 20 milliseconds. One might be 10, one might be 20. But anyways, we can take both of those frames and slow their transmission down to 100 milliseconds, right? And now we've gotten a ton of bandwidth back from the CAN bus, from all of our follower Talons. Now, on the general devices, like on the master devices rather, sorry, we can take our general feedback frame and speed it up. We can speed it up from its default to 5 or 10 milliseconds, depending on what we're trying to do. And because the way the followers work is that every time the master Talon sends out a general frame update, they copy that frame and output it to their motor. If we speed up the general frame on our master Talon, we've now effectively increased the update rate on our follower Talons as well. So that's one thing that I do recommend doing for high bandwidth control applications, right? Like a path following drive base. On the master Talons on each side, speed up the general frame to 5 milliseconds after you've slowed down all the slave frames. Now, one thing to note is that you shouldn't slow down the frames too far, because if you slow down the frames too far, the library has a built-in timeout. And if it doesn't receive a frame within that time period, it'll generate errors and sometimes will cut off operation of the motor. Now, similarly, on the master Talons, we can take the control frame and speed that up to 5 milliseconds, so that now we can send it updates at 5 milliseconds, and it will also update the followers at 5 milliseconds, right? And after slowing down all of our slave transmissions and speeding up our masters, our CAN bus utilization metric should actually still drop from default configuration, right? So that's one thing to kind of look at, like a little trick. Now, let's talk about what does actually all of this do for us. Like, we've talked about all of the boring stuff first, about not doing any kind of motor control yet. Let's actually look at what we want to use them for to accomplish. So we want precise motor control, right? I think that's why everyone's here. Is there anyone who's not here because they want to move things precisely? Okay, so we have a couple different algorithms we can use for this, right? We need things that are motion control algorithms, things that move our system based on feedback accurately. So the algorithm that we're going to talk about now is PID. Most of you guys are familiar with PID? Show of hands. Pretty good. Okay, I got this wet rag here. I feel like this has a recommended dry time, so we're going to replace it. So PID, right? PID is a control algorithm that uses feedback to accurately control your motor. You have a set point, meaning a value that you want to achieve from your motor. Like, you're telling your motor, I'm here right now, and I want to be over here, right? So this is your actual value. This is your set point. It's kind of like a request. So we'll look at position PID first, right? That's what most teams do when they think of PID. They use it to control position. So with PID, we have three terms, P, I, and the D. So the P term is the proportional term, the I term is the integral term, and the D term is the derivative term. Now, what does that really mean? How many of you guys are familiar with second order differential equations? 3, 4 people. Okay. Well, we're going to talk about that. And most of you probably won't like it. Anyone that knows who it is definitely won't like it. So we can summarize this with a few simple formulas, right? The control algorithm. Let's start by looking at the P term. So for each of these terms, it's going to have an associated gain value with it. And what that gain is just a multiplicative factor that we are going to multiply our value by to give us our motor output, right? So the gain term associated with our P is Kp, lowercase k, uppercase P, Ki, and Kd, right? So every term has its own associated gain. So for the P term, our P term is just our set point, board is bouncing, it's giving me like depth perception weirdness. Set point minus actual times our Kp. So what does this equation actually say? Any takers? Yes.
Taking the point where the point that you're currently at, you're multiplying it by Kp is like a factor. So like, if you're multiplying this, you want to get there like fast, and then like slow down. Like as your actual changes, it's a smaller number that you're multiplying by.
Right. Exactly right. I know what you're saying. So let's say that we start at 0, right? So one thing to keep in mind with PID is that it's an iterative process, just like all things that we should be thinking about in real-time control system design. Everything is iterative. We always look at it at the perspective of how long it takes our loop to iterate before we enter our loop again, right? So we have a PID that's running at 10 milliseconds, right? So every 10 milliseconds, this statement gets evaluated. So to start with, let's say our set point is 1,000, right? The units are arbitrary. The units can be anything. Let's say our set point is 1,000. And when we first start our control, our controller starts at 0, right? Our motor's at 0. So our actual error here, this calculation is just the error, is 1,000 times our Kp. And that's what gets output to the motor. Right? So that's our motor output. Now, that's going to be a pretty big value, right? Like if we had our Kp value of 1, right? We just said our gain was 1. Our motor output is 1,000, right? So for WPI library type motor controls, your output's only negative 1 to 1, right? For Talon SRX, when you use it in the code, the output is only negative 1 to 1 as well. But internally to the Talon, its output is minus 1024 to positive 1023, right? So that's its native units of pulse output. So here, we would have our output as 1,000, right? So in Talon world, almost full output. Now, another 10 milliseconds goes by. Our set point's still 1,000, but now our actual is 100. So now, what's our motor output, right? It's 900. It's a little bit less than what it was before. Now another 10 milliseconds goes by. Our subsystem's really cooking. And we're at 900, right? So now our motor output is only 100, and we start to slow down as we approach where we want to be. Make sense? But another 10 milliseconds goes by, and now we're at 1100. We've gone too far. What happens now? Well, now our motor output is negative 100, right? So now we're going to go back. But because PID is signed in its calculation, it will automatically have direction that it can follow. But we still don't want to go back and forth between 1100 to 900 the whole time. We want to get to 1,000. So we need a couple more terms to get rid of this type of oscillation. So the calculation for the I term is the sum of the error times the I gain, right? We're okay, everyone, that this plus equals is the sum. And now, this is where I feel like a lot of you guys are going to argue with me regarding the way to approach the I term gain. It's 0. It's always 0. Never use I for FRC PID tuning. It's just not worth it, right? With this type of gain, right, I, it is way too easy to get what we call integral windup, meaning that our system has been away from the set point for way too long. So every iteration that it goes through our loop now, our error is just a running sum of craziness, right? So we're going to be like such a large value that the I term is going to saturate your motor output, and then it's going to go all kinds of crazy. So what happens when we get steady state error, right? Well, we'll talk about that in 2 minutes. Give me 2 minutes. Then if I forget, remind me, because it's actually part of the presentation. So the D term is the calculation of our error minus our previous error over our time delta times our D gain. So this term is very useful in applying aggressive motor outputs in a change in time. So the greater your change in error is in a smaller amount of time, the greater output your D term is going to contribute to the motor output entirely. So with all of these terms tuning, like we have our P gain is 1, let's say we set our D gain to 2. Who knows, that might be awful, but let's just pretend that we've gotten the 980, right? And now our system has reached what we're going to call steady state, right? Every loop iteration that we go over, our motor output from the P term is 20 out of 1,023. It's not enough to move the system due to the friction that's on our subsystem. And nothing's moving anymore. So we're at 980, and we want to be at 1,000. We've now reached this 20 error as what we're going to call steady state error for our subsystem. What happens when we have steady state error? Well, nothing. You have to decide if it's good enough, right? Because if I have my elevator from this year's robot, right? I want to place cubes on the scale. So my elevator is here, but it was actually supposed to be here. Does that really matter? Does that little bit of steady state error matter? No, it doesn't matter. If it does matter, raise the set point just a little bit, right? There are other ways to accommodate steady state error than using the I term, which can provide too many issues, right? And there are a lot of people that are going to argue about that and tell me that I'm wrong, which is fine. I would love for you to argue with me about it so that I can tell you that in my experience, this is better to be 0. And you can do anything you need to do with the I gain being 0. Almost anything. So now another approach is that if I'm here and I want to be here, what if I raise my P gain a little bit more, right? Instead of 1, let's set KP to 1.2, right? Now my motor output, instead of being 20, is just a little bit more, right? Maybe that's just enough to move my motor a little bit more so that now that I'm at 986. Right? Is this acceptable here? Probably. If it's not, maybe a little bit more P. There's other control approach to strategies to use than iGain. A lot of teams get hung up on, well, that's not the way PID is really supposed to calculate, and it's just a PD loop. Well, you should use the Dterm because that's what it's there for. Just don't do it, because I've already done it, and I'm telling you, it's not worth it. Yes. Why? So you're saying that the friction in the system is building up more and it can't move it?
No, that can't.
So I think he's saying once you get propagation of error after it's over.
No, error will not propagate. Right? Every time you change the set point, this entire calculation starts over, right? So your steady state error will not propagate from calculation to calculation once you change it. It will only be from your specific instance that you're at right now. Make sense? Right? Because yes, question.
Oh, I had a question. So, with that equation, doesn't the value that you sent to
Yes.
Right now, it just happens to be like, oh, it's 1,000. So, like, isn't it like does that change? Can be changed?
Yes.
So, it would,
so you would choose a gain.
that makes it like
Well, you would choose depending on what type of PID you're tuning, right? If you're tuning the PID in the Talon, then yeah, you want to be between minus 1024 and 1023. But if you are in the WPI library PID, which I really don't recommend anyone use ever, then you would want to be between -1 and 1 for your motor output, right? So that okay. Now that brings up the question.
Yeah, of the PD. So how would you handle the situation? We had this trying to get our turning command, right? About turn 90 degrees. So we have our motor speed set to 0.35, keeping the set they say it won't go far enough. But we go to like 0.4, and it's way overshoots, and we keep messing with the value. We can't like consistently either overshoot or undershoot it. And
So I think what you're experiencing in that system is friction, right? So one way to compensate for that is to cap your output of your PID term, right? Have a higher P term, but only allow maximum motor output of 0.5. Or gain scheduling, meaning the closer you get to your set point, right? Once you pass a threshold, switch to a different set of gains. So those are two approaches. And then the third option, which I will give you, is like way more complicated, but 100 times better. You would use your encoders and your gyro to do it, right? You would use everything. And using your encoders, you would do some kinematics calculations to determine the number of ticks that you need to rotate. And then you would use the motion profile control mode on the Talon to generate a profile for how far you need to turn. And then you would regenerate that every 10 milliseconds, like every loop iteration, until your gyro said you were where you needed to be. You can find an example of that in the Cheesy Poofs 2017 code.
yeah,
Turn to heading.
they're a little above my head.
It's not, I promise. You download it, I guarantee you'll be able to figure out, but you have to spend time staring at it. I spent at least 7 days just staring at the code. Yes.
So if you decided that if you're like maximum amount away from your set point, as in like you're closer to moving it and you want to start moving at like 50% speed, let's just say you're using the -1 and 1 just to make it easier. Would an alternative to tuning your speed just plug everything into that equation and solve for K just basing out for it, or is that
If you wanted specific constraints for finding your gain like that, then yes, you could do it that way. And now I'm going to tell you, when we talk about tuning the PID, don't do it that way. But you could. So, all right, now we got dry time. Oh, done. Okay, so now we want to talk about tuning the PID, right? So this is where we come into what's a second order differential equation, right? Well, a second order differential equation is a fancy equation that where a lot of things are changing. How many of you guys have taken calculus so far? How many of the students? Okay. So you will take calculus, and you'll like it. No, you may or may not, but
It's fun.
it's fun. I loved it. I thought it was great. Everyone thought I was psychotic. You know what? They still do. So with calculus, you're not going to learn about second order differential equations in high school. You probably aren't going to learn about them in college unless you're an engineer, and then you're going to learn about them way too much. So we have this equation where multiple different things are changing at once, and there are multiple different ways to solve this type of equation, right? And what it boils down to at the end is that after we've done a whole bunch of math BS that no one really wants to talk about or do, we get 3 different states that our equation can end up in, right? That our system can end up in. And these are the states of operation of our system based on the gains Kp, Ki, and Kd. So let's say this is our request, right? This is 1,000. And now this is our actual that starts at 0. So this is just a steady line, right? Our request doesn't change. We're always at 1,000 for this example. So we talked about our system was oscillating between 900 and 1,100 in our first example, right? So it would look something like this. And what this type of equation would be called, right, this type of state for the system, this would be known as underdamped. Now, if our terms were tuned such that P was reasonable and that KD was really, really high, we could end up with a situation that looked like this. Right? And this would be overdamped. So we kind of are very, very, very slow to rise, and we take forever to get where we want to be. Now, we end with the last state of our system, where we kind of we go maybe a little bit past where we want to be, but we settle right about where we want to be. And this would be called critical damping. So the majority of subsystems that you tune, you will want to tune for critical damping, right? With critical damping, we have a reasonable rise time, and we don't overshoot really too much. This kind of is a bad drawing because it's a little bit much overshoot. Just pretend that's less overshoot. Right, we don't overshoot too much here, and then we're kind of just where we want to be. So critical damping is really what we want to achieve. Why wouldn't we want underdamped for our system? Yes?
If it's underdamped, it oscillates too much. Never going to settle on, but it's always kind of be bad as
Can also cause damage, right? It doesn't do what we want it to do, and it can also hurt our system. Very good. Most people miss the hurting of the system part. I'm way too familiar with it. So yeah, we don't want continued oscillation around our set point. Why wouldn't we want underdamped, or why would we want underdamped?
We wouldn't want underdamped because it takes forever to compute the request and like wait kind of valuable time by the time we kind of use that's better, like less detrimental for the system than.
Can you think of a scenario where you would want underdamped all the time? I mean, I'm sorry, overdamped all the time?
Maybe for like an elbow.
What if we have something that we want to move that's very fragile, right? Super fragile, and we don't want this little overshoot here that comes down, right? We could look at approaching the system from an underdamped tuning set point. Not the best solution for doing that, right? But it is a solution. It's a simple one. But okay, so for critical damping, this is what we want to achieve, right? It gets us to where we want to be pretty quick. There's really not much overshoot, and we stay where we want to be. How would we go about tuning this system? Well, some people are like, well, you have to model everything using physics, build it in MATLAB, then generate a Simulink model and generate the gains for the system, and you have to use the Dterm. No good. Way too much work, way too much time, and then when you're done, it still doesn't really work well, right? So everyone will argue about that, right? Everything in industry pretty much has a Simulink model, and they all build everything using MATLAB and Simulink, and they generate everything from a theoretical standpoint. But they're spending millions of dollars on research, and everything is manufactured within specific tolerances, and then things aren't going to really change much over time because maintenance is actually performed on them, unlike FRC robots, right? So with FRC, you can't expect the robot to continually perform like a Simulink model when you're building it with a drill press and a bandsaw and then beating the crap out of it on a field every day for months, right? It's not going to match the model probably after your first match, let alone your first competition. So model is really kind of out for me. But we can tune the system experimentally. And what I mean by that is you just choose a bunch of random numbers based on some educated guesses, and then tune the system within the best operation from those numbers. So to do that, we have a tool that we developed that's a PID tuner. Right? Basically what we built was a LabVIEW dashboard that will make this graph for you, right? It's a continual running graph of your request, which the robot transmits to the dashboard, and a continual running graph of the actual value, which the robot sends to the dashboard. It graphs it, and then we have little text boxes on the side where we can enter the gains for our system and also the set point. We type in a set point with our gains, we measure the response, and then we do it again until we get the operation that we like. Now, this tool is public. It's available on our GitHub. I really don't like it. I think it's a really lousy tool. We made it. It's bad. But we're making a much better tool that will be released soon, which is actually pretty. It's developed in C# instead of LabVIEW, which no one should use LabVIEW. And it also uses a better bundling method for data transmission, right? It uses this stuff called OSC, which my friend Todd put me onto, which really I thought was trash before, but it's actually not bad. I've come to like it. But the data transmission from the robot is all UDP, right? So we don't use things like network tables or anything the WPI library provides for us because we want it to work. And then we send all the data as a continual UDP stream to the dashboard and the robot, so that if we ever miss a packet, there's another one coming. It doesn't really matter. And then we can build this continual plot, and then the dashboard itself sends back the gains to the robot so that we can tune the system. So the way you would want to tune the PID, well, first off, has anyone heard of the Ziegler Nichols method of tuning PID? A couple people. Okay, too complicated. So there's too much math involved in Ziegler Nichols method, because you want to, Ziegler Nichols method says increase the P gain on the system until we have a steady state oscillation, and then determine the period of the oscillation and do some other math to say that your real P gain is that, and then your I and your D term are also that. First problem, there's I gain. Second problem, way too much math. I don't even want to know what the period of this oscillation is, let alone do some other calculations based on it. So the way I would recommend tuning a PID is to increase the P gain until there's a small amount of oscillation, and then increase the D gain until the oscillation goes away. You might have to lower the P gain a little bit and then readjust the D gain. Just choose some values that make sense. Now, one thing that people do making mistakes tuning the PID system is they will always choose the same set point. Like they'll go from 0 to 1,000, and then from 1,000 to 0, and then 0 to 1,000. Every time they make a change to the gains to see how it responds. Choose different values. Do some short travels, some long travels, right? Sometimes go 0 to 200. Sometimes go 200 to 2,000. Sometimes go 2,000 to 20,000. Like it depends on what your system range is, but choose different length intervals and different spots in your system when tuning it, and then try and choose gains that are an average of all that, that make the best response for the system within your desired range of operation. Does that make sense? Are there any questions on that so far? Okay. So now, what I'm going to tell you is never use PID to control your subsystems, right? So after all of this that I've been telling you about PID, don't use it. We're going to use it at an underlying level, but you don't really know that it's there so much, right? The Talon will know that it's there, but we're going to use a built-in mode of the Talon called Motion Magic, right? You're familiar with Motion Magic. You sounded excited, right? Who knows Motion Magic mode? Yep, a few people. Okay, so Motion Magic mode is really just PID encapsulated within the Talon, where they automatically will generate a motion profile trajectory from your actual position to your set point position. So what is motion profile? It's magic. It is. It really is magic. That's a good answer. So motion profiling, the way to think of motion profiling for a motor is that if we want to control the position of the system, then we will do it by controlling the acceleration, the velocity, and the position all at once. So the way this is actually done is that the velocity of the motor is what's controlled. We control the acceleration by manipulating the velocity we request with respect to time. And then we control position by controlling the velocity and integrating it to reach the position that we're at desired, right? If we've moved this fast for this period of time, we must be at this position. So the way the Talon works is that it will generate a trapezoidal motion profile acceleration trajectory, where every point of your trajectory has an acceleration, a position, and a velocity at every single point, right? Every 10 milliseconds, there's a new acceleration, velocity, and position. Now, tuning this is just a little bit different, right? It's the same thing that we talked about tuning the PID, which is why we talked about it. But it's more, right? There's another term for our equation, and it's our feed-forward term, right? And our feed-forward term is just the KF gain, which is also associated with the feed-forward term, times our set point. So the feed-forward term would never be used for a raw positional controller, right? Because it's a constant output. If your feed-forward gain was 0.2 and you had a set point of 1,000, you would have a minimum motor output of 200, right? And it would just constantly be running, and it would run right past where you wanted it to be. So you never use a feed-forward for position. But for a velocity control mode, when there are things on your system that resist the force of the motor rotating, right? It resists the torque, it resists the acceleration. We use a constant minimal motor output to help us reach our velocity, right? So if you have a wheel spinning at 10 meters per second, and you want to keep the wheel spinning at 10 meters per second, you wouldn't have a zero motor output. You would need a small amount applied to it to help it keep going, right? Reasonable? So that's what the feed-forward term helps us do. And it doesn't do all of the velocity benefit, like it doesn't do all of the velocity calculation, and it doesn't do all of the velocity output, but it will help stabilize the PID component so that the PID is responsible for a much shorter delta, and that will remove things like oscillation and things like that. So using motion magic mode on the Talon, there is a procedure they tell you to find F, right? And what they say is to measure the maximum speed that your subsystem can run, and then do a little bit of math on the actual max encoder ticks that the system is reading, and then say, well, that's the F gain. But it doesn't always work that way because we can't always get a system running at the maximum speed. We have an arm on our robot that if we ran at the maximum speed would just crash into the elevator and break into a million pieces. It's happened. So right. Driving is a different story, and we're going to get to that later. You have to actually do the driving at full speed, so I'm sorry about that. But for small subsystem and manipulator calibration, we can do calculation of the F gain. Right, so the calculation for our F gain regarding motion magic, right? Motion magic F. Motion magic F is our KF equals, let's see, we have our max RPM. And this is the maximum speed that our motor can spin at, right? We can find that on motors.vex.com, or we can also find the motor characteristics for those motors that we're going to talk a little bit about, or good gearbox design, depending on the torque curve output of the motor, right? We can't do any of the stuff that we want to do if our motor is completely overloaded and the gearing in our gearboxes isn't high enough that we can move our system with enough torque, that it's not going to stall out and trip our breakers. So we have our maximum RPM divided by our gear ratio. Divided by 600 times 4096. This is all wrong. This is supposed to be in the denominator. All right, let's see how we can fix this without awful rewriting all of that. That's let's see. I'm just actually double checking it because I did it from memory and I want to make sure it's right. It's good. So this 1023 comes from our maximum output of our Talon, right? This we talked about, minus 1024 to 1023. Now we're dividing that number by the maximum RPM that our system can spin at. This is a ratio, not a ration. 600 is 100 milliseconds per minute, right? Because our native units are encoder ticks per 100 millisecond, but our motor speed is in RPM, so we have to do a unit conversion. And then this 400 here, this 4096 here, this is the native encoder ticks per revolution.
Aren't there some, we don't have an issue where we had a practice spot and I don't know why I keep it.
Yes.
So the practice spot is sort of like
1024.
Yeah, 24, and then that one, 96.
And the reason for that is that you always want to use a crossover electronics magnetic encoder. If you're not using it, you didn't listen to part 1. So always use the crossover electronics magnetic encoder. This number will always be 4096 if you use that encoder. If it's not, then there's a serious problem. Call Omar immediately and start yelling. Omar's the guy that makes the talents, and we're like really good friends, and at the same time, I feel like I make him so mad all the time. So this calculation for F is actually very, very accurate when using motion magic only. If you were to tune a velocity PID and you did this calculation to find your F gain, it'll be pretty good, but it won't be good enough. And the reason for that is that this assumes your system is purely linear, right? And your system is not purely linear. So when you were tuning a velocity PID, you would want to do it experimentally like we talked about. Except you would start with the F gain, right? You would choose a set point that's within your operating velocity range. Now, what I mean by that is that because we already said that this is really not a linear value, we would want to choose a set point that is where we expect it to be running. Like if we have a system that we say we want to run at 12 feet per second, and it's going to spend most of its time running at 12 feet per second, you would choose your set point for tuning KF as 12 feet per second. Then you would tune KF so that your, for F tuning, you would have your set point here. You would tune KF such that you were about here. Right? You wouldn't want to get all the way to your set point using just the F gain. Because if you do, and then you would try to apply P and D for actual corrections, then it's going to go crazy. But if you tune it so that the P and the D term only have to bridge this gap, then you're going to have a very stable operating PID. So you would start, tune F till you get about here, add P until you get about here, right? And you get a little bit of oscillation, and then add D. Now, when you're tuning a velocity PID, the important thing to remember is that you will never get rid of all of the oscillation because of the way velocity works, right? You're trying to keep something spinning at the speed that you want, and it's constantly slowing down, and you're constantly speeding it back up, and it's still constantly trying to slow down. You can get pretty close, but consider like a ball shooter, right? You're going to have a lot of factors influencing the speed that it's spinning at, because every time you try and shoot a ball, you're going to take a huge dip in the speed, right? So if we have a ball shooter and we tune it and it's running like this, our set point's about here. Every time you shoot a ball, it's going to go like this, and you're going to try and get back up here again. Now, the problem, if we had an I term like this, every time we took a dip like this, it's going to want to wind up. So you would dip, and then it would come back. And then you eventually would get back to where you want to be, but it's just not something that you should do. So tuning without I avoids issues like this for tuning velocity systems. So what systems on the robot would we want to tune using a velocity PID? Any ideas? Any guesses? What's that? Wheel shooter, right? Ball shooter, inline wheel shooter. Always use velocity PID. Don't just ever try and do open loop percent V-bus control. And what's that? Drive, right? We want to do an advanced path following algorithm. We can't use motion magic in the Talon because it only does straight lines, right? We can't use their built-in motion profile arc mode because it's really not great. And we want still accuracy. So we're going to use our own algorithm that uses velocity control on the Talons itself and then does all the outside calculations around it, right? The motion profile arc calculation on the Talon is pretty good. It's a great way to do motion profiling if you don't care about accuracy, right? It's good. It's very good. You probably get plus or minus 5-6 inches of repeatable accuracy. But that's not good enough for me because sometimes you have to be tighter than that. Sometimes you want to be plus or minus 1 inch. And that's not reasonable using that algorithm over a 40-foot path, right? It's just not something that it's meant to do. What it's meant to do, it does very well. That's not what it's meant to do. So yes, we want to use velocity control on the drive base to implement a more advanced path following algorithm. Now, what other modes of operation do we have available to us, right? We've talked that we have percent output, right? We're going to call this allowed modes of motion control. So if you use any mode of motion control that's not on this list, I'm not allowing you to do it. But I suppose I don't really have any say, but I really don't recommend doing it. So percent output. What would we want to use percent output mode for? Any ideas? Teleop drive, right? Joystick control. Perfect usage for percent output, right? So when you do velocity control on the drive base, you wouldn't keep it in velocity control all the time, only during autonomous. Once autonomous ends, you switch to teleop drive control with percent output control. Any other ideas? What about like an intake, right? We don't really care about what our intake is doing. So maybe an intake, we just run it at max speed. And then because we've properly chosen a gear ratio for our transmission, it doesn't stall when we go to suck things in. We can just run it and then it sucks things right in the robot. What about velocity control? Right, we talked about drive base, auto. What else did we say? I don't actually remember. Shooter, wheel shooter, right? Thanks, Brando. Okay. Oh, that's upsetting.
Just have the third, fourth line, the first line.
this setup. I got to get one of these at my university. Okay, so we have for set output, velocity. Okay, now we also have motion magic. What do we use motion magic for? Elevator. Arm. Things. Right? Pretty much everything that needs position control we'll use motion magic for. What about current? Well, I don't know if you'd want to use current control for a shooter because you don't really have any guarantee of the speed that it's spinning at. In order to shoot accurately, right, we want to use velocity control for our shooters. But you could do current limiting, right, so that you don't overdraw current on it. But what would we actually want to do current control PID for, right, where we'd want to target current that's absorbed by the motor? Yes. Something that you intend to stall out, right? Like the desired mode of operation is that it runs, it gets something, and then it's stalled. You can use current control for that to stall against whatever it is that you've collected and keep a very small force that holds it in, right? So something like an object intake. I'll give you an example. On the intake wheels on our robot this year, we had a sensor that anytime we had a cube in the robot, it would run a current control PID on our intake wheels to target the motors sucking the cube in with 2 amps of output to the motors. That way there's just a very, very small force that the motors apply to the cube. Yes?
Could you just do that with like so make you apply yourself that you see the increment side, and you just press it, it runs at like 50% speed, so it's like.
Why do you not want to do that for yourself? You can't tell. What your drivers are being attacked. They're being attacked. They don't know what's happening. Your robot is just completely defended. They're being bashed in. They have other things to worry about. Anything that you can automate that the drivers don't have to think about, the better off you are, right? So a lot of people say, well, our drivers can just do that. But they shouldn't have to, right? The drivers should only focus on driving. Once the cube is in the robot, it should have the cube. Yes?
I just feel like an elevator, because last night we had our elevator ready for max height, and the motor first started smoking.
Okay, so you were running against like a limit, like a hard stop, or was it just holding the elevator up?
It was pulling the elevator up. But, like, yeah, no, not good.
So it was a 775 Pro?
No, actually.
What was it?
It was, I don't know.
Okay. So sometimes if you have systems that are heavy and it's holding the elevator up, it overheats, right? Because it's constantly running. And what I would say is that you probably would want to choose a little bit higher, like a lower gear ratio, right? So that the motor has more torque and it's able to hold it up a little bit. It would be stronger, but the motor would have to work less hard, right? So you'd want to choose a gear ratio that's more suited to the subsystem. The other part of that is sometimes if you just let stuff stay under PID control, holding it up, it's going to burn stuff out, right? It's not meant to run like that. It's only meant to run short periods of time.
I should have heard it. Just overworking.
Right. It's probably tired, right? It went through a whole season of usage, and then it's like, you want me to hold this here? What?
I don't know if this is related, although I remember there was talking about brake mode and like mode, and there's like 2 different ones, and there's like can you explain?
So brake and coast mode, right? Brake, maybe your elevator wasn't in brake mode. Maybe it was having trouble holding it up.
Yeah, probably.
So there's 2 modes on the Talon, or really any motor controller, but we're only using Talons. There's 2 modes, brake and coast mode, right? In brake mode, the leads, when the motor is not being driven, the leads of the motor are actually shorted together so that the magnetic poles will resist each other and the motor will try not to move, right? You can still force it to move if you push on it, but there's a lot more resistance than if you have the motor operating in what's called coast mode, where the leads are not connected to anything, then the motor can just freely spin, right? So brake mode, the magnetic poles resist each other and you have more resistance to motion even when the motor is not being driven. Coast mode, the motor is just freely movable. Now, with Motion Magic PID control systems, I would definitely recommend using brake mode so that you have more accurate control of the system. With the drive-based tuning for path following, I would probably recommend using coast mode because the algorithm that we're going to use is much, much more advanced and does all of the other stuff for you. Motion Magic, use brake mode. Well, what if our intake? Well, maybe we want to use brake mode so that when we have an object, it's holding it, right? So that it holds it a little bit better if we have the object and it's being held. Or what if we have, if we just want it to like spin completely freely, then we would use coast mode. It really depends on the system design. So it's important to understand how the modes function so that you can choose whether to use it or not. Good question. Yes?
Question about like, I think it was the percent, the percent, if you have a certain percentage of whatever.
Percent control.
Percent control, yeah. So what our old programmer he did was he made like they using macros, so like you have our driver drive, then like do like a certain path you want to replicate in auto, and then use the data from that. So it's like make a macros for auto, and I know you use percent. He was trying to make a feedback loop with gyro and encoder feedback, but there's no issues with that. I didn't fully understand. Can you explain to me? I don't understand.
So the problem with, yes, I do understand that. And the problem with doing that is that it's just wildly inaccurate because you can't replicate what a driver is actually doing in auto.
Yeah, that was an issue. Very inaccurate.
So that's part of the problem. With percent output mode, using this for any kind of like accurate control is not, it's not possible. It just can't be done. So with using encoder feedback, we'd want to use another type of control mode so that it's now repeatable. So the idea of having drivers drive a path and then having the robot replicate the path, it's a good idea, but it's just not really doable. So even when we generate a path for the robot to follow autonomously, it's going to be a path that's specifically geared for the robot to follow it autonomously, right? If drivers were to take the path, they would probably take maybe a slightly different path, just because when we're tuning the path for autonomous, it's going to be like fully optimized. Like it couldn't be as replicated by a human because it needs to be perfect, right? And the humans aren't perfect, unfortunately. So we're going to try and target the most perfect path possible. And I think that's one thing that some people who do path following miss, is that not only do you need to tune our control algorithm, but we also need to tune the path that we're choosing, right? So some paths may be more achievable than others, and some paths might be more difficult than others. And you want to choose the path that accomplishes what you want it to do, but you still want it to be very achievable for the robot. What's that? I have not.
It's a book about Microsoft team that they were competing in 2009, and in the book I was reading it, it had like a part where they were like, I don't know if they were at Worlds or they were regional, but they were doing like their audit, they were doing paths. So they had like, I'm not sure if you think about that.
Way before my time. I started FRC in 2015.
Yeah.
And everything that I've learned regarding this stuff has been learned since then. So if somebody did stuff before that, I probably don't know about it. But it sounds very cool. Nowadays, the de facto anything of anything is Team 254, in my opinion, right? They are,
This have way more advanced stuff.
yes. So they've just now released a new path following algorithm from this year that blows all of the other path following algorithms I've ever seen out of the water. Like, it's just better. And my estimation is consistently roughly 10 times better than anything else I've seen before. The path following algorithm that we used this year was their algorithm from 2017. And the new algorithm is 10 times better than that. It's just amazing. And it's all based on dynamics models of the robot that I said, of course, you know, models are useless, right? But it's not really modeling. It's measured gains, right? They have a mode that you use to characterize the drivetrain, and it performs like some operations. It'll drive, it'll turn, it'll do some stuff, and then it'll do a bunch of calculations, and it'll measure these gains, right? And then you output these gains as constants into their calculation, and then you put a couple other things in, like the weight of the robot. You have to measure a couple other constants, and then you run the path following algorithm, and everything just works. It's like, it is magic. It's pure magic. It was a big reason why they went undefeated this year, right? There are a lot of other things that they do that makes them go undefeated as well. Yes.
Another question. So when we do like autonomous control, we usually do like multiple groups of command groups. So like you go forward, you turn, you go forward again. So like there's this issue that it never like thinks that it reaches the set point. So like the is finished thing never returns true. It never moves on to the next command. So I was thinking like how you can solve it is by like increasing the tolerance. You can make the tolerance bigger. Like even if it doesn't quite reach it, the tolerance is more like it still gets the tolerance so it thinks it reached it. Like do you think that's like a good strategy for trying to just to increase the tolerance?
Absolutely.
Also, like how much you increase the tolerance?
That is something you need to tune, right? That's what we talked about, tuning paths. So yes, absolutely. I completely agree that increasing the tolerance is a good strategy to approach that. You don't want to increase the tolerance too much that bad things happen. Now, another thing that you can do is add a timeout, right? And that if you've waited for more than X period of seconds here, you must be done. So continue on to something else. That's another thing you can do. And the third thing that I will say is that don't use command groups from WPI. Anything that WPI has, don't use. That's my recommendation, right? So there are a lot of things that they do that are good. There are a lot of things that are good. And unfortunately, we don't see those things because the things that are good are all happening on the back end, right? The stuff that we have that's available, like command groups and their tasking library, all of those things are limiting, right? They're good for very, very basic, simple stuff. But they're not good when we now want to do more. Yes, question. I thought you raised your hand. Sorry.
Oh no, I was just thinking like if you don't use the
Okay. So now we write our own tasking library, right? So we're going to write. You don't have to write your own, right? You can use ours. You can use the cheesy groups. It's literally just copy paste. You have a thing. And then you put other things in the thing, and that thing executes the things you want executed. I mean, it's very simple. Like I'm kind of playing with the description of it a little bit, just because people make it out to be so much more complicated than it actually is, and I think that limits people to think that like we can't do this because it's just too complicated. But it's not. It's just not complicated. But people think it is. So.
Can you talk about that just a little bit more? Use the WPI stuff. What are the have a jump the more realistic trade-offs?
Well, I mean, the more realistic trade-offs of not using WPI command group options is that you can do more things, right? It's you have complete control over the actions that you execute and the way that they are executed. So one thing that the WPI library has limitations on is that all of the things that you schedule to run in its loop are all limited to being synchronous with updates that are sent to the driver station, which only happen every 20 milliseconds, which is not fast enough for good control, right? So now If we spawn our own looper, right, we can do it in our own thread. We can even use the WPI notifier, right, to do our updates, but we can specify a time period. We don't have to wait for certain things to occur. It just gives you more complete program control regarding those things. So how many of you guys here use C++? Okay. When you guys have a young team?
Yeah.
Okay. What are you switching to? Java? Okay. What about, how many of you guys use LabVIEW? Well, that makes me happy. Not a single person. Perfect. Okay, so those of you guys who are using C++, definitely recommend switching to Java for the simple reason that it's easier for kids to learn and it's easier to do a lot of high-level things with less time. Because in C++, you can do all the same things that you can do in Java. You can actually do more things than you can in Java. But you are not given anything, and you must write everything on your own. Like if you want a tree, you have to make a tree. You know, you can't just say in Java, oh, look, there's a library called tree. We can put data into this tree and have the data structure sort everything for us. No, in C++, you must build the tree, you must build the sorting, and then you have to build the way to get the data out of the sorted tree and still not have it blow up, which in C++ is really difficult sometimes. So if you're using C++, don't do it. As good as it is, for FRC, I really think that Java is better. It's just easier to teach kids with. You can teach them more things in less time. And then they can be more successful and be motivated on their own to learn even more things. And then once they've reached like a established knowledge in programming and basic programming, then they can learn C++ probably on their own, right? But it's not a great language to start people off in. Question so far? Yes?
So I have a question about, there's running things in parallel during auto. So it's kind of two kind of separate but the same question. So one of them, the issue we had was trying to, there were two issues. We were driving and raising the elevator during auto as like a parallel, right? We were using the WPI stuff. One of them was we were going for the scale and we were driving and lifting the elevator. It made our head of robot really nervous. He always thought we were going to tip, and so he basically made us grab it. And the other issue is with like currents. I think he might have bad batteries. So like, we've been having a lot of brownout issues, and it's like a really bad issue. Like towards the end of the match, every match, there's like browning out. So
Okay.
Like, even in auto, it's just like it's low.
So bad batteries are a huge caveat of FRC, right? Do you have a battery beak?
Yes.
Okay. You want to check on the battery beak that the internal resistance of your battery is 0.015 or lower, in addition to the battery being charged fully, right? And being charged fully meaning like greater than 13 volts. Now, if your internal resistance is high, there's a higher likelihood that your battery is not great. But the internal resistance changes during the charge cycle, right? So you'd want to check the internal resistance after charging the battery, unplug it, let it sit for a few minutes. Don't just immediately check it. Check the battery after it sits for a little bit, determine the internal resistance if it's still a good battery, and then use it. If it's good, don't use it if it's bad, or use it if it's bad, but no, it's not going to work. So another issue that is not just bad batteries is that if you're running a lot of things at once, like you're trying to drive and move the elevator, you have to understand that every system now draws more current from the battery. So if you're trying to do too much stuff at once, you're going to draw down the current on the battery, and it's not going to be able to supply enough current. And what's going to happen then is that the voltage is going to drop. You're going to experience brownouts. Your systems may not move the way you want them to, and then bad things happen again. You want to make sure, especially in autonomous operation, that you're only running things that you need to succeed. So one thing you can do is if you have air on the robot and you're running an autonomous and you're trying to execute a path in autonomous, turn off the compressor, right? While you're following a very difficult profile or trajectory, turn off the compressor.
Entire elevator is on a solenoid. So actually, we deploy the elevator in auto, and that's what pushes the elevator forwards. A lot of for starting configuration, they have like the weird like the selector that can lift up. Ours doesn't do that; it just stays straight. The entire elevator moves.
Okay.
We have to have the air go up so that if you can.
But you can use pre-charged air, right? Like you have an air tank on the robot that stores the air.
Yeah.
You have enough air that you can do certain operations with before you run the compressor.
So you suggest maybe running the compressor with the telly off. Also, get the telly off and then do like
That's just one strategy to save some current consumption from the battery. You might need the compressor in autonomous if you have a lot of operations that are using air, right? And you run out of pre-charged air, then you need the compressor to recharge your air tanks. But you can turn the compressor running on and off, right? You can do it in the code itself. You can disable or enable closed loop control on the compressor, and that will turn it on or off using the PCM. So that's another strategy to save voltage. The other thing that you can do is to actually profile everything, right? So the more things that you profile, the less sharp, the fewer sharp movements that you make, the more forgiving your tasks are. So that's another thing. If it's profiled, you have fewer sharp corners. Things that are less sharp draw less current. Is a rule of thumb.
the whole elevator thing. We were running parallel, but kind of moving and the elevator flipping became like not ideal. Should we end up accidentally going on the platform or whatever? We shouldn't, but the auto does weird things.
Well, okay, so the other thing is that you said that your elevator was smoking when you let it sit for a little while. So maybe you just need a little bit more power, a little bit more torque, right? And you can get that from changing the gearbox on the elevator to have a little bit more gear ratio.
I'll suggest that for a second. But they probably won't listen.
They definitely won't listen. That's my experience too. The mechanical people never listen. So
We have one more competition, so I love that we're done.
Mhm.
So
So at motors.vex.com, there you will find graphs for every motor available for FRC use. And on that graph will tell you the speed of the motor, the current that the motor draws while operating under those conditions, the torque of the motor, and the power output of the motor at those conditions. Every motor has a specific set of characteristics. And it's important to choose a motor that is good for the operation type that you expect. Or if you are specifically using a type of motor because it weighs less and you need whatever characteristics that motor provide, then it's important to design the subsystem to support the individual caveats of those motors. So I'll give you an example of the 775 Pro motors. They have a lot of torque and they are very fast. Actually, I would totally use it for an elevator. We did. But
I know the really bad issues with using that for elevators.
well, they probably didn't design the gearbox to support those motor characteristics. What's that? We use 775 Pros in our elevator. But we did a lot of time tuning the gearbox gear ratio because there were issues, right? In addition to our elevator just having ridiculous amounts of friction, but that's another problem. The 775 Pro is a motor that likes to operate very high in the RPM range, right? High RPM, high efficient. Term is like, as the RPMs keep going up, they keep getting more efficient. Then it's steep fall off. But you want to run the motors pretty high up in their efficiency range. You want to run the motors at a good part of their torque curve, right? You don't want to be running the motor in range where the system is overloading the motor, so you're drawing more current. It's not able to move things as well and you're drawing way too much power, right? You're going to trip your breakers, and then that's bad. You're going to burn out the motors. That's bad. We want to try and operate the motors as close to, I generally say somewhere around where the efficiency and the torque curve intersect, but sometimes you want to operate higher in the efficiency range, especially for motors like the 775 Pro. You want to run those motors almost near the free speed that they can run at. The free speed being the maximum RPM that they can spin at unloaded, like not connected to a system. So you would choose a gear ratio for your gearbox that allows you to run the 775 Pro within that roughly that RPM range, so that there's enough torque that the motor can raise your subsystem. Now, for things like an elevator, because our elevator had tons of friction, it's not something we were able to model due to the fact that you can calculate lifting weight using motors and a drum all you want, and you're never going to be able to accurately model the friction in that subsystem. So what we did was we just kept changing the gear ratio until we found one that worked. Similar to experimentally tuning the PID, right? Except instead of gains, this time we're tuning it with gearbox gear ratios. For other subsystems, you can tune the gain. You can tune the gearbox gear ratios mostly based on calculations, right? If you had a subsystem, right, that you were climbing, say a climber, right? We were climbing and we have a drum that we're going to use to pull a rope. When we pull the rope, we want it to be able to lift X force from the robot, right? So that if we have a robot that weighs 150 pounds, we want to be able to calculate a gear ratio that allows this motor to lift this much pounds using this drum and this rope, right? Yes.
Your system, what was the friction? Was it literally? I mean, is this if this is rubbing solvent, I don't want them to get too distracted, but I'm curious about which parts of the system were troubling and which parts weren't.
So our elevator was a single mast elevator, which did not have a single bearing in it. All of the pulleys had bronze bushings, and all of the stages of the elevator were connected together with nylotron E-blocks that were like machine slots that the I-beams of the elevator went through. And then we had two drums on a rope, and the rope would pull. It was a continuous elevator, and the rope would pull. Now the elevator, first off, E-block, if everything went perfectly, it would still have a ton of friction because the E-blocks bind right in the metal where it slides on the nylotron. There's friction there. There's friction in the pulleys. There's friction everywhere. But in addition to that, as this time went on, the bronze bushings, we had little bronze roller bearings inside the last stage of the elevator as well. Those wore flat spots on them, so they just grated against the elevator instead of rolling. The E-blocks wore a little bit, so that now there's a lot of slop in the elevator, and it racks back and forth like this, and then it will just sometimes come down all the way to one side, bind against everything on the way down, and there's a lot of friction there. So if you try and move, and there's also just a lot of friction everywhere. It's everywhere. The gearbox doesn't even move if you try to move it by hand. You have to literally like throw your whole body weight on it to pull it down. Part of that is just due to the mechanical advantage from the gearboxes and the drums and everything across the whole system. Most of it's not. Any other questions? Yes. What's that?
Thank you for living that.
Oh, you're welcome. It was really painful, but I hope that you got something out of it. So, yes.
But is it like a road that you set talent to, and like how do you get around it? Like, does it run the PIDs by itself, or do you need to write something that?
It does everything by itself, which is why it's great, right? So that's why that's the magic part. It comes in, it's all built in. So inside the Talon, there are sets for all of the gains, right? You have there's options like config KP, config KI 0, config KD, and config KF, right? You set the gains. Yeah, you type the gains in. You have to do the tuning part still.
So in the web interface.
Don't ever use the web interface. Never ever use the web interface. Always set all the values programmatically because the web interface is awful, right? Don't use it. Sometimes values get stored in there. What's that?
Yeah, we've had some issues with it.
You used to, I think, be able to set the max output in the web interface, and sometimes people would be like, why isn't my Talon running more than 0.5 out? But it's because you set 0.5 out in the web interface, and you can't undo it programmatically unless you reconfigure everything.
So then how do you do it?
All through the code. There's all options, like all methods in the API, like I was talking about, the config KP, config KI, config KD, config KF.
Just put them all in one place.
Everything. Have an init method in your code. Set all the gains every time the robot turns on. Every time you deploy code, everything gets set. Never use the web interface. So then, once you've set all your gains in Talon, then when you call the set on the Talon, you just call Motion Magic as the control mode. And then the value you send to the Talon is the number of encoder ticks that you want to target. Right? And that's in their native 4096 ticks per revolution unit. Yes.
Question. Our gyro we use like to help with turning and stuff. So we ended up having to put it like, because our Rio is like at an angle, so we like put it like our electrical one's like diagonal, so we have to like have it extended and then like upwards and stuff.
Using Navix?
Yeah, we have to like extend it out and have it like upwards and straight. But anyway, is there a way to like reset the angle? So we have like a zero encoder method, but we don't like have a zero like near the angle.
Right. Okay. So yes, there is a set zero reset in the Navix API. But if you're not at the zero plane of your robot, then the rotation won't be quite right. Right. It has to measure in one of three axes on the gyro.
That's why you have to extend it out, so it's just it's horizontal.
Right. So then what you have to do is you have to enter the world calibration mode on the gyro, in which case it will use gravity measurement from the accelerometer to say which way is down and then automatically determine which way is your yaw value. And the way you do that is you hold the calibrate button for 5 seconds, then you let go, and then you wait until the yellow light comes on solidly. Then you push the reset button, and then you don't touch it or move for like 30 seconds until the yellow light stops blinking, and then only the green and the red light are on. Then it's world calibrated itself for gravity, and then you can get the yaw value using the software in the correct angle. But you do have to have it in one mode or the other. You should never have it in an angle.
Yeah, no, that's what we had this. Sorry, our
Extended.
Rio extended, so we ended up having to get like extended.
Right. Any other questions?
Did you ever do motion profile with the native motion profile?
In the Talon?
I'm sorry, in the.
Never. Don't ever do it.
It's not worth the effort for you.
Well, we did it. And it kept having this thing where 60, 70% of the time it would work, and then the rest of the time it would start driving and then stop. And then it was like buffer underrun or motion profile underrun error. And I was like, this is crazy. We can't ever have that happen in a competition. So we stopped, and we just never did it ever again. And then they did motion profile art mode, and the same thing has occurred with that, is the profile underrun errors and those types of things. So I don't like that. The fact that it can ever have that happen to it makes me sad, and I will never use it. Yes? Motion profile.
So there are three modes.
Yeah.
They all kind of have very similar names. There's a thing called motion profiling, which sort of predates these two magic modes.
I see.
And then motion magic has this trapezoidal profile.
That's the good one.
Well, that's really, really smooth. We did motion profiling with raw motion profiling before Steam Breaks. didn't have quite that problem, but it was hard. And then there's this arc mode, which is for things that are other than straight lines, but it's also.
So if you ever are going to use motion profiling mode for the Talon, for path following, you should definitely use arc mode, right? And the way arc mode works, so, okay, let's go back. The way motion profiling works is that you have a left and a right trajectory, right? You would have a left and a right Talon master. You could preload a profile onto each side of the robot, right? You could generate that trajectory using a number of different tools. We happen to make a tool called CyberPath SRX, which will automatically generate profiles for the motion profile mode of the Talon. It's freely available on GitHub. Even though last time I tried to access it, it didn't work, so I got to figure that out. And what that does is you have a robot, right, with a left side and a right side, and every trajectory is calculated, like every point in this trajectory is calculated every 10 milliseconds, and the left and the right side are individually controlled. That's motion profile mode. There's no way to synchronize the two trajectories in the Talons, right? They just run independently, and you pray to God that they both work about the same time, so you roughly get where you're trying to go. Now, there's motion profile arc mode, in which you designate a full master that has control of the left side, the right side, and also the gyro. So you need to use a pigeon for the gyro because it has to be connected to the gadgeteer port in order to feed data to the master control Talon. And what the main Talon does is it takes the left sensor, the right sensor, adds them together, and divides by 2 to say that's where I am in the middle. Like that's the center position of the robot, which is sketchy. It works, but it's not what I would say good. But now what it does is with motion profile arc mode, you specify a single trajectory. So every point has a position, velocity, and a heading. And then the robot will have an auxiliary PID in addition to the motion magic key type PID that does the control that is additive for the gyro. Again, it works, it's kind of simple, and at best it's sketchy, in my opinion. But for a really kind of pretty simple, easy way to implement something that's really complicated all at once and make it available to a ton of people, it's fantastic. But if you have time, I wouldn't recommend using that. There's just a lot of caveats with it. And then there's like a motion magic arc mode, and I have no idea how that works. Never used it, never seen it. When I went to look about it, they didn't have an example posted yet. So, yes.
So first, for elevators, we're trying to obviously the different elevator heights this year, right? So there's different scale height. Most common at the bottom. So we have like, I don't even know what we have honestly. I don't really understand. I don't understand it. It's dumb.
That happens a lot.
But basically, what's happening is, so the governor's cup, it worked fine. It went to the which height the scale height was supposed to, and it did okay. We got a few cube things. And then we didn't make any changes at all to the code involving the elevator height. And then here goes river rate, and it just goes to scale height every time. Well, it just goes to max height, just stalling out. And just like.
By velocity encoder.
Yeah, but yeah, but it's reading encoder values. Like we checked the smart depth, we're reading encoder values. So it's like, how do we kind of troubleshoot this and like actually make it not stupid?
So one thing that is good for troubleshooting is the web interface, right? As long as you don't set values in the web interface and you only use it to read values, it's a great tool. because it can tell you exactly what's happening. It'll tell you the mode of the talent. It'll tell you the output of the talent. It'll tell you the position value from the encoder, and it'll tell you the velocity, right? Everything you need to know to troubleshoot what's going on. And then the only way to troubleshoot it really is to go through your code step by step and check it every step of the way to see what's happening. All right, so that's just code troubleshooting technique. Welcome to FRC.
So this is I sympathize with some issues. It probably wasn't the code that changed.
So it came unplugged and then we put it back in. So I'm sure there's something that caused probably what happened. I just can't figure out what.
Part of the encoder was eating itself and started to find out.
Probably.
We've had encoder slippage, right? We've had bad connection, had CAN bus overload, had limit switches that we've rolled past, and didn't realize we rolled past them, and so when we come on again, all of these things happen.
Yeah, the limit switch, automatic limit switch control.
For the talent?
The talent is great.
Don't use it. It's bad.
We didn't use it.
So what's the story?
Right past and crush the switch.
So if that would happen, then you're not using the closed loop control portion of it, right? So if you have the encoder and you're using it and all of your stuff, even if something goes wrong, right, you can use soft limits to limit based on encoder value if you don't want the subsystem to move past a specific portion. But if you were to use limit switches with the talons, you would want to make sure that the limit trip portion of it was well outside of the drivable range in either direction. Right.
Safety, so we didn't
Right.
launch
Full safety. I still.
First scenario where the encoder is not returning as many ticks as it should, you're going to overshoot, and the soft limits are on that point.
I would recommend doing more control based on current. If you're at that point, I think you are advanced enough to move on to the next step, right? So you can do other things that, if say you were to create a software monitor loop, right? In this loop, its only operation was to read back values from the subsystems and check those values. So if your monitor loop sensed that your elevator was drawing more than 30 amps for greater than 3 iterations, something's wrong, disable the elevator, throw an error, try and perform a corrective action, that kind of thing. So the limit switches are good for basic operation if they're outside of your desired operation range. But if you're using limit switches correctly, you can probably do more.
Started using, trying to use current friction problems, so using current to Hallmark.
So for subsystem design, now we're getting into whole good subsystem design stuff. Current homing is a good way to do it. I don't recommend using current homing for 775 Pros. But you can, but they're allowed. You'd have to set up current limiting, and you can manipulate all the values and change them. I know you said you had friction issues, so using current limit, you probably thought you were at home because there was so much friction while driving.
And it would change as it wore.
Right.
It changed too drastically, so I'm going to keep up.
So what you can do is you can couple current with velocity, right? So you say, I'm drawing greater than this period of, drawing greater than this amperage for this period of time, and my velocity is 0, right? Because when you're current homing, you expect to stop at the bottom. So then your movement is less than, never say 0 because it's probably never 0, but less than 10 ticks per rotation or whatever.
What do you consider the kind of a reasonable update rate? Or what's a good delta T in your experience?
1 millisecond.
And you don't think you're pushing things to do you think that's at the border of what the robo reader can handle, and are you really worry a lot about other things going on in the robot at that point?
Yeah, So
Height limit?
here's the
What
secret.
table? Okay.
you would never ever ask the RoboRio to perform an update at 1 millisecond. You have the talons, all the native control is performed at 1 millisecond, right? So if you use all of the native controls in the talon, those all get updates to the motor at 1 millisecond. Then you run the RoboRio as like a wrapper outside around those loops. And then you would use that probably at like a 5 or 10 millisecond update to the talon, and then the talon will update 5 or 10 times for your single update. So think of the RoboRio as providing an absolute value that you're trying to achieve, and then the talon provides 5 or 10 relative values in between each absolute update.
And is that talon rate, is that the frame rate, or is that independent of the frame rate?
Independent of the frame rate.
That's an internal computation.
Internal control rate for the PID. Think of it as similar to the concept of a phase lock loop, if you are familiar with that, right? So you have an absolute signal that kind of updates your relative every X period, and that kind of provides you back on track, right? The talon, it doesn't need that, right? If we were Motion Magic, we actually do differential set updates for every set point that we choose. So every time we go through our loop, if our set point's not different from what it was the last time we requested, we won't send another value to the talon to save on bandwidth in the CAN bus. Because if we're sending a frame to the talon every 10 milliseconds, that's no different from the frame we sent last time, why bother sending it? So we do differential set updates, and that removes those dead values from our CAN bus, gives us more CAN bus bandwidth back. Make sense?
So almost everything you said makes sense, but I have to admit the whole frame concept on CAN has made me a little crazy.
So think of every frame like a packet, right? And
Is it point to point, or is it broadcast?
it's broadcast.
Okay.
So it's broadcast. Every device in the CAN bus receives that packet. But every device in the CAN bus also has filters that configure which packets are allowed into its accepted, here's my incoming packets buffer. So if you're a follower talon, in that filter, the master talon is allowed. But some of the other talons are blocked, right? We don't need those data, so forget it. In the Rio, every data packet that comes from a talon is accepted, right? We want all of the data. So because we think of them as packets, because that's how it functions, but at a hardware level, it's really just 2 wires that are going high and low all the time. So that's why the utilization metric is so important, because if you're above, I really say you want to stay below 85, below 90% utilization, because above that, things start to get right. 50, you will never get below because of the way the RoboRio instantiates their keep alive safety packet. It's total BS. Like the
Fast.
what's that?
It's fast. It's like,
It consumes a lot of bandwidth. Like it's not quite 50%, but with everything else that's going on the CAN bus, you will almost never get below 50%. Your base utilization metric is like 55%. So a safe value to target is about 70%, right? 70% during full operation mode is good.
And all of the devices on the CAN bus are pure. No actual master. I understand that they can behave.
There's no actual master. So it's not like I2C where you have master slave. It's nothing like that.
So everybody just spits out status packets occasionally. Everybody listens for those things. Nothing.
Yep. And the only time a device knows when to transmit is when other devices aren't transmitting.
just sheer luck.
Right. I mean, it's
It's like all of us.
Kind of like
Ethernet is different, because if you overload your maximum, like if you're trying to send gigabit data at 100 megabits per second, you're going to buffer everything, right? So it's all going to get sent eventually, just slower until you fill up the buffer.
okay, fair.
There is not that.
It's like half duplex. Right now, or
Well, what it is exactly is it's canvas, right? It's a weird mixture of a whole bunch of different things. It's just there's so many interesting things about it.
But while this, so there's this frame rate where these frames flying around at some maximum rate. But then on the Talon itself, it's got its own internal
Correct.
clock.
Yep. So all of these things would be triggered as a periodic update from like a slow output loop, right? So, and then the Talon runs on a very, very fast loop, right? So every 1 millisecond, it's updated. There was actually a problem with the firmware a couple of years ago that there were some velocity calculations that the Talon was not able to complete within its 1 millisecond update time. And I was tuning the shooter wheel, and it was oscillating like crazy. And I was like, Omar, there's something going on here. He's like, no, it's fine. And then, like a day later, he emails me. He's like, oh, hey, try this new firmware here. We think we found something. And I loaded the firmware. It's smooth as butter. So those timing updates in the Talon, not only are they like really fast, but they're really important that they are fast. Because if they're not fast, you lose all kinds of control.
You update the firmware the robo regularly.
Well,
Do that every year? Do you
the firmware on the RoboRio you have to update every year, right? Because they release a new competition firmware version. So when you image your RoboRio, it loads like FRC 2019 V18 or whatever they end up with when they come out of the beta operation. So every time you get your new LabVIEW installed list or whatever, you have to image the RoboRio for FRC 2019 competition use. And then that has all of the libraries and everything for FRC 2019. Periodically throughout the year, if there is an issue, they will release a RoboRio update firmware, and you should always apply the firmware updates as soon as they're available, because they're generally, like, they won't release a firmware update unless there's a really big problem.
This year it was a huge issue in the like console write processing. They made it take like 70 times more CPU time to do any console outs.
Is this between like the 0 and 5?
This is the RoboRio P, I think it was 18 and 19.
So I think you mean Talon firmware?
Talons are different.
No, I don't mean Talon. I mean RoboRio.
Okay.
So I'm asking because my inclination was to get the firmware for the RoboRio anytime I saw it. That was sort of my impulse.
That's
And then I
definitely
read something that they said, don't worry about that. What comes with the kit is fine. If that's all you need, it's okay. So I thought that was
not true.
I looked in the FRC distribution, and there were two firmware numbers. There was one that was like 3.0.0, maybe it was .18 or something like that. But then there was 5.0.0.0.
It's extra.
Well, a little too many
At
zeros
least
on that.
just the version number of the driver station. When it comes to that. So you connect it, it spits out a version on that screen. That's the more reliable. This year the update was not mandatory, but if you
This year the update was not mandatory, but you should.
Okay.
It's not like they never.
I was surprised they should too.
Anytime a firmware update is released, they like are loath to release a firmware update. So if it is released, it's necessary. Now Talon firmware is very interesting, right? They have a lot of different versions available. I always like to use the latest version, but know that if you always use the latest version, you might be doing a lot of code rewriting because they're not always backwards compatible. But they do make new features available, which I like to use. So I always update constantly. But yeah, the concept of CAN bus framing, around 70 to 80% is reasonable. More than 80%, you enter the danger zone. More than 90%, stuff doesn't work.
Because the clock and cycle set on.
It's all transmit based on the start of the frame. So
Be totally quiet until somebody speaks, and then everybody just yells.
Exactly.
On it.
in addition to that, there are multiple different data rates that are supported by CAN bus, right? There's 125 kilobits per second, 250, 500, and then the robot uses 1 megabit, I think, which is the CAN 2.0B Bosch spec. So there are a lot of different data rates available. Now, because of the change in data rate is also going to affect the baud rate, so that if one device is listening on a different data rate than all the other devices, it will actually short out the whole bus and nothing will work. Because
dynamic goes down.
they do not. Question?
Explain a little bit about waypoints, because like that's something I've seen like when going through data with other code. Doesn't really make sense to me, but someone explained it out generally. Yeah, I'm just kind of curious more about like what it is and when we use it.
So, in order to talk about the concept of waypoints, we have to look at the field as an absolute coordinate system. Right, so our scale is here, our switch is here, and we'll only care about this half of the field because waypoints we really only care about for autonomous. Right, so our robots start here, here, and here. So now, a waypoint is really just a position on the field, right? This is a waypoint. A waypoint means a point in the path that the robot is going to be following, right? It's a point that the robot gets to an endpoint by way of this point, waypoint. Now, the waypoint coordinates can be dependent upon how you have set the coordinates of your field, right? Depending on what tool you use to generate your paths. Some tools have like this here start at 0, 0. Some tools have it split so that like this is 0, 0. There's all different kinds of stuff. So that the actual coordinate of the waypoint is dependent on the tool that you're using. However, a waypoint is just a point on the field and a coordinate. And when we were to generate a path, we would specify waypoints at every juncture that we had that was critical, right? So we wouldn't want to put a waypoint here. We would put a waypoint here, and we would say the robot drives to here, and then using the Cheesy Poof's 2017 tool, if you were to do waypoints in this way, you would choose here, and you would choose this point to have a radius of like 45. And then it would automatically make this nice curve here for you between these two paths. And then between here and here, you could put a radius of 45, and it'll automatically make that curve for you. Now, there are a few different algorithms that you can use to generate the in-between portions of these 2 points here, right? So the Cheesy Poofs from 2017 use line arc interpolation, right? They draw lines, and then they also draw arcs. It's pretty simple. But from their library from this year, and also their library from 2014, they use what's called quintic Hermite splines to do interpolation between multiple different points. And that is a really big amount of math, right? It's just kind of like a lot of high-order differential equations and high-order polynomials that can approximate a lot of different places along here that will provide you a smooth curve between 2 points. And in addition to that, you can add them together from point to point, right? So a waypoint separates those different paths. There's another method of path generation between waypoints that uses something called space curves. And the implementation of that can be a little sketchy because there's a couple different ways to implement it. But as a general rule of thumb, they generate faster than quintic Hermite splines because of their characteristics for millions of iterations. And when you do things like this, there are sometimes millions of iterations depending on how many points are in your path. Space curves allow you to do section-to-section paths. When you generate spline curves, sometimes you'll generate more of a path between points at once. So you would do this whole thing. space cars, you can do smaller portions of it. Now, there's a way to speed up the calculation of quintic Hermite splines by removing constraints on the derivatives that you place, right? So when you generate quintic Hermite splines, you want, say we generate the curve as a position curve, right? We have our waypoint that has a position on our field, and we want the spline to go from our positions here, right? And it's all in terms of our position. We would say the first derivative of that spline is our velocity curve along that path. And then the second derivative of that curve is our acceleration curve along that path. Originally, in 2014, Chitipoofs tried to, well, they didn't try, they did, but they set the first and second derivative of those curves to be continuous so that there were no discontinuities in the path. The calculation to do that takes longer to find a proper equation that fits all of those constraints. If we remove the constraint of the second derivative being continuous, and we only care about our original spline and the first derivative, the velocity, being continuous, and we say, well, the acceleration doesn't really need to be continuous because we don't control that anyways, we can speed up the calculation a great deal.
Do you pre-calculate these, or do you actually calculate them?
Both. So they are pre-calculated. There are a couple methods of dealing with that, right? So the algorithm that we use this year to deal with that, all of the paths were predetermined, but they were generated as we went based on where we ended up, right? So we didn't expect that we were where we wanted to be. We said, where are we actually? Now I want to get there.
In autonomous, how will you decide where you at?
Odometry.
Just encoders.
Encoders and gyro integrated and filtered.
Just those two.
Mm-hmm. So if you integrate those and filter them well, you can have a very high degree of accuracy. Luckily, Chitipoofs have made this class called the Robot State Estimator, which is very well integrated and filtered, very accurate. We're looking into creating even more accuracy using that class by adding something like maybe a Z or some kind of SLAM algorithm, and then injecting that value as like an absolute reference as a slow update rate, maybe using something like a Kalman filter to bring all of our values back to where we expect, like an actual update. Kind of like GPS for the robot, right? Except on a smaller scale. So our algorithm, we're in autonomous, we generated our path. Now, as we follow it, we might not be where we want to be. So there's a controller called an adaptive pure pursuit controller, which will help you achieve your path, right? It's like it'll help you traverse the path and adjust and correct for errors in your position and curvature based on what's actually happening.
So the thing that the difference there is what you measure from the encoders and the gyro
To what we
versus what
expect.
the calculation was expected.
Now, the new algorithm has all some kind of crazy stuff that I don't even really know how it works yet, but it's all some kind of nonlinear feedback stuff. I'm not really sure. Like, it's all. I understand that it's based on all the calculation stuff, but I'm not sure how the corrective portion of it works yet from where when you're not where you want to be. But it's really accurate. It's scary. It's scary accurate.
Considered more sort of, I guess, more sophisticated sensors to include in this, like, bounce a ladder off the wall or off the switch. I mean, does that?
Yes.
Have you noticed that added any value? Have you really pursued any of that and seen it succeed or fail, or not?
We want to pursue it, but the problem that we keep running into these caveats that we just haven't figured out how to get around. Well, the first thing I should say is that I don't really think that we've seen anything that we couldn't accomplish with what we have now. So is it really worth spending a whole bunch of time dumping in more accuracy to something like a LiDAR that's pretty difficult to implement? It is from the cool side of things, but from actually making stuff do more things than we can now, I'm not sure it's going to do that. The other thing is that on the FRC field, LiDARs don't really work very well with Lexan. So it's like the clear sidewalls, right? It's the plexiglass frame for the field. So the laser is just going to kind of shoot through that, and it won't be a hard edge. So you won't get that as a metric. So now if you're trying to generate positional data, you're reading something maybe out here, which is not the same as the wall. So the LiDAR is not, I don't think it would be great for SLAM, but a camera could work for SLAM in weird ways. It's just, it's a lot of work for, I think, very minimal improvement. Any other questions? Yes.
This was actually good for it. Repeat, if you say not to use the built in WPI stuff for like the so a little bit like what the alternative. Right now we're using the WPI like the sequential parallel. Do that
So within our code, we have a framework, right? And our framework is very, very similar to the Cheesy Poops framework, but we each invented it kind of like simultaneously next to each other. And then when I went to look at their code, I was like, oh, look, they did the same thing I did. And then once I saw that, I just straight copied everything they had. So they have this class called a looper, right? And what the looper does is that's basically like the WPI task scheduler, except we have more control over it. The looper is like an outer class where we can now take a bunch of loops and register them inside our looper. This is going to be stuff that we run continuously, like the drivetrain, maybe an elevator, maybe an arm. And all of those are individually controlled, but inside of the looper, they all run sequentially. Now, we have, in addition to this, in our main thread, an auto mode, right? Auto mode executor. And what that does is that runs an auto mode. Now, for the auto mode executor, we have an auto mode, which basically takes up the whole auto mode executor. It's just another layer of abstraction that's used for implementing these things in a bunch of different ways. Now, inside of the auto mode, we have actions. And this is what's similar to the WPI libraries run sequential, run parallel, right? All of our actions inside the auto mode run sequentially, but inside of an action, we can make it parallel or series, or we can make it parallel series. We can do anything we want, right? It's infinitely layerable so that you can build it as you want, and then you have more layers of configuration. You could have these 4 tasks run sequentially with this task in parallel, right? So there's just unlimited layers of configuration that you can have if you use your own framework. And then if there's stuff that you want to do that you can't do, you can just add it in. Whereas with WPI library, it's a lot harder to add stuff in because no one really knows how it works.
So the framework's all kind of there.
It doesn't exist until you copy it from GitHub and download it. Then it's there. And then you can do all this stuff, right? So your classes, on the YouTube video from last week, it was really boring. It was terrible to watch me talk about how to build path following in your robot. I literally gave a step-by-step tutorial of what to copy and paste from our code to implement the 2017 path following algorithm, which includes the auto mode executor and the looper. Right, so there's literally just a tutorial video of my screen as I copy and paste stuff into the program, and then the robot moves, and everyone's like, woo, woo, and they were happy. I was beat and exhausted, but it was cool. It took me about 2.5 hours of straight copying and pasting at the end of an 8-hour presentation.
Right, I think that make that trade.
What's that?
I said, considering how long it took to write it, make that trade.
Me too. I did make that trade. Any other questions?
Back to the following parts and lines and all that. Talk a lot about odometry, gyros, motors. And I'm sure you guys are engaged in this talking naked. That's your drive source. Trust the encoders. I always, in my mind, make it require slippers. So how much do you trust the encoders?
I would not trust them at all. My best advice to you is don't use Mechanom. It's not something that you could do like this accurately. If you were to use Mechanom, you would have to implement something that was more absolute, like SLAM, right? So you would have to do something with the camera or something else that you could trust as a more reliable data sense than the encoder. Now, you could also put like that's what I was thinking. I was just thinking, yeah, you could put like a mouse or something down there, measure X, Y, unbounded screen size, right? And just measure the position as you drive around. We've actually talked about doing that. It's not a crazy idea. It is crazy, but we've talked about it. You could also put like an Omni wheel in the center of the robot with an encoder on it. Or you could not use Mechanom.
So we've actually, right, we've used it 2 years ago, and we found that the advantages of having it for the drivers is really huge. And we were actually able to get cross-field view placement on the scale with Mechanom strafing. But it got flipped, right? I mean, it was, and much of last year's, the previous year was actually more successful one. But last year, a lot of what we did ended up being just
So, honestly, I know a lot of people disagree with me about it, but I've already made it clear that people disagree with me about it. It doesn't really faze me. It's one of those things I just kind of like plow through, independent of how people feel about me. But I really don't recommend using Mechanom or Swerve or robot drivetrains. Like, there is nothing, in my opinion, that you can accomplish more with either of those drivetrains than a lot of other teams have proven they can do without them, right? So the only year that we used Swerve was of my time, was my first year in 2015, which was god awful. And it was just recycle rush, right? Terrible. We used Swerve and we didn't need it. And everyone would say, oh, well, the drivers have so much more maneuverability and control. But, I mean, I think it created more problems than it solved because it was heavy. So we didn't have enough weight to make other stuff that we wanted. It was difficult to control in autonomous, so we had trouble doing anything with autonomous. That being said, there is a way to generate 4 independent profiles for Swerve trajectory and then have them do all kinds of crazy Swerve path following. But you shouldn't do that. So I know that you don't have to listen to me and that you all are free will. But there's just too much other stuff, I think, going on that it's just not worth building a non-standard type drive base, right? I'm not saying that won't work. If you run, so what a lot of teams do that use Mechanom or Swerve is they ignore the ability to Mechanom or Swerve during autonomous, and then they kind of just will execute a standard profile using like a standard differential drive kind of skid steer approach. And yeah, that'll work. But now you have all this drive-based stuff that you're not taking advantage of and people want more. I don't know how to make this really work very well for Mechanism. I don't know. And I don't know, I wouldn't personally, but you know, it's up to, if you figure out how, I'd love to include it. Like if you figure out how to make this stuff work, we'll post it right on the GitHub. You're like, boom, solution now.
I have seen some stuff. I haven't seen Encoders or I haven't seen everything on too, but I know 2009, way back, there was because of the slip surface or whatever. There's a few that were really successful with WordPress that year. But like there happened some games where
Control, like motor control, was also a different ballgame back then. We didn't have the tools that we have now that allow you to do more advancements with less complicated types of technologies and stuff. To be honest, what I always use is like de facto standard of stuff, and I don't want to sound too much like a fanboy, but I always look at what 254 does because they're very successful, right? And there's always somebody out there that we can learn from. So 254 has had tons of success using their 6-wheel drivetrain that they've built for pretty much almost every game that they've competed in, and they've consistently been one of the best, if not the best robot in the world every year without using all these other weird drivetrains. The one year that we built a 6-wheel drivetrain that worked like 254's drivetrain, we were the most successful robot that we've been in our entire history of being an FRC. We were able to do everything that we needed to do. We didn't have any severe problems. Our drivetrain was great. We were able to play defense, offense, anything we needed. We were able to survive defense against other teams, which has been a problem for us in the past. Our drive base from 2017, last year, we built an 8-wheel drivetrain that had some weird funkiness. It was all messed up. It was terrible. By the end of the season, the whole thing was bent into like a pretzel. And then they're like, oh, by the way, you have to go compete at IRI. We're like, oh, gotta rebuild the whole thing. So, you know, that this year they built a very interesting drivetrain with Omni wheels on the outer, which gave them even more capability.
They helped a lot. One time we didn't have those Omnis in the back, it was impossible to drive. You had to like 3-point turn for everything. It was really.
Well, the drive-based geometry is always a consistent issue, right? And a lot of teams solve it by using Omnis or using Mechanism or Swerve or things like that to turn in any direction. But another good solution is a drop center drive base, right? That you have 2 wheels on the bottom that are able to pivot. And that as the robot turns, it can kind of rock back and forth and pivot around that point. So, I mean, a lot of what we're getting into now is just opinions on subsystem design and stuff like that. And I promise that none of you guys will be able to change my opinion. I'm a very stubborn person. But I would love for you all to try. Any other questions? So let me just make sure that I covered everything that I wanted to cover today. So I really did want to show you guys the graphs from motors.vex.com, but I'm not really sure how to get the projector and stuff running. It's not really important at this point. So look it up on your own, right? Figure out how to look at those graphs and understand how to choose gear selections based on the amount of torque that you need at the output of your gearbox. Choose gearboxes that are good for the motors. Understand that different motors have different useful characteristics, like the operation range for a 775 Pro is different from the operation range for a sim. As far as motors go for using an FRC, I really don't recommend using any motors other than the 775 Pro, the sim, the mini sim, and then rarely the bag motor. Any other motor should be replaced with a 775 Pro. And the bag motor, most of them should be replaced with 775 Pros. They have their uses sometimes. The 775 Pro is the same as the red line. It's literally the same. It's a clone. Very good. You mean the back mount red line encoder mount? Okay, yes. So that's why I don't recommend using it, is because not only that, however, the signal from that is what I was talking about, has sometimes been a problem in the tower. Like it has overflow that can occasionally cause the positive velocity to turn into a negative velocity. I'm sorry, position, I think, because of the way it works with the ticks. I'm not really sure what actually happened with it because I haven't been able to test it myself, but I was part of this group where everyone was freaking out about how, oh, this is velocity does wraparound or whatever.
Why are we intaking a full RPS all the time? Why are you using an encoder? Like, I mean, they don't work.
They don't work. Well, if you use the Crossroad Electronics magnetic encoder, they will always work as long as there's, green on the light. Yes.
So I think on that we had one that turned yellow. It was too far away. But we could pull it back out, so we just
So yellow is an ambiguous operation state, right? Because sometimes if it's yellow, it's okay. Sometimes if it's yellow, it's not okay. Right? It's supposed to be that anytime it's yellow, it actually is okay. And then when it goes red, then it's bad. But yellow has a range, right? When it's green, it's good. When it's red, it's bad. But like there's all this yellow space in between red and green. And the farther you get towards red, the worse it gets. And the closer you get towards green, the better it gets. So the best bet is just to always make sure that it's green. If the magnet got like sucked all the way into the shaft and you couldn't get it out, try and get it out. And the way you can do it, you can try and get something like another magnet that you can stick in there and kind of pull it out. Another thing that you could do is that if the shaft is hollow, you could drill a hole behind it and then push it out with like a pick or something. There's always a way to get it out. It's just, it depends if it's important or not. But you definitely want to try your best to always operate with the encoders in the green light range. That being said, for those of you who use Vex Pro versaplanetary gearboxes, which I highly recommend as the only gearbox you should use for small manipulator control, due to the fact that they have an encoder stage that you can just stick on the output shaft right after your gears. All of those encoder stages have yellow lights for the magnet. Like they're all built in. They all come from the factory with yellow lights. They work. But you can take them apart and shim it so that the magnet's actually too close to the encoder in those. You can actually shim it out a little bit so that it turns green. And then you have perfect operation. The Vex Pro gearboxes, it's nice. The best part about them is the integrated encoder stage, really, and they're configurable regarding gear ratio selection. So when you're doing the math for the motor, you can choose the gears. A lot of people are happy or love to use the PG71 gearbox, which is very fragile and breaks a lot and is also exceedingly difficult to change. So I would recommend avoiding those. We actually had, for the year of 2015, which was like the year from hell for me, the PG71 gearboxes were used to do the steering on our drivetrain, which was swerve. So in our quarterfinals match at IRI, one of the gears inside the PG71 gearbox sheared just for no reason. The motor seized up, stopped turning, and then the robot got on fire. So
I'm laughing. I'm sorry that happened.
It happens.
It caught on fire.
what's that?
It literally caught on fire.
It like sparked flames and then it died, thank God, but it was bad.
Said 2017, said we were at a competition, and there was one of our weird vehicles. We thought that because we were running one side of the taking timer against a motor that was pre-load, we kept running saw some magic smoke. It's a melting wax. So,
Stunned.
It's hard.
also, IRAD.
Not good. Any other questions? All right. Well, I think our time is pretty much up for the day. Is there anything else that anyone wants to cover or talk about today before we dismiss? Is there anyone who wants to argue with me more about my opinions? You can always argue with me after. Question? Programming an H-Omni drive. What about it?
Does the swerve program work?
You would have to build your own odometer. I think it would be more accurate than Mechanup. As accurate as Swerve, more accurate than Mechanup. But you would have to build an odometer that was able to take into account both your forward translational movement and your sideways translational movement and integrate it to provide you your actual position on the field inside of the coordinate system to do path following with that. Very simple fix for that is to get rid of the H. Just try it. Yes. There are no dumb questions here. What's up? What do you mean a perfect curve?
Because you said like put a point back. So you have to come to the lowest amount of distance.
Well, you could do that by adjusting it with tuning, right? But your radius, it's not really a degree value, right? This is more of where's the center of my circle here for my arc. With tuning that radius, you would want more than the smallest distance traveled. You'd want to make sure that the robot was able to smoothly achieve this path. Using the radius value is more for achieving a smooth path so that you don't have any jerky motions and you can make the path following more accurate. So does that make sense? It is, but it's also there to make it smooth. So like it serves a dual purpose. The way you would adjust for the shortest distance travel is by moving these 2 points and then adjusting the radius so that you could have, like you could cut the corner here if you really wanted to get close. Right, you would adjust for that in other ways. Double bank.
What do you guys target from start when it would gaze down? Or do you see you're just making drivers and flush?
So they're never ready, and we're never polished. So,
So we have something come.
I don't think our robot actually worked until week 3 this year. Luckily, our first competition was week 3, and they're still like bolting things on and unbag time at the competition. They're like, "Hurry up, we got to put this on there." And I'm like, "Well, can't do any tuning yet." So it's one of those, because of the way FRC is. There's always like a time crunch. But immediately, the very first thing that we do when the game comes out is we select a drive base. And there's always one guy on our team who's always like, "Swerve drive." And I'm like, no swerve drive. You know, and every year we waste at least 2 weeks determining which drive base to use for the game. And we always nowadays end up using a standard drive base. And we just waste all that time. So what I would suggest is just skip that part. After that, I have already begun working on the code for next season now, right? We're trying to train our new students. My actual lead programmer graduated this past year. So this is going to be a really difficult season because basically I had to do nothing this entire past year. He did everything, which is great. But it's not going to be the case next year. We're going to have to do a lot of training. But we've already begun working on the code, right? So my goal is to have all of the code for next year's game done before we even know what the game is.
Then you publish it.
We will publish everything that we've done by the end December 31st. Copy and paste it.
Thank you for your efforts.
So most of what's going to be done, you're going to have some kind of manipulator, right? Either an arm, maybe an elevator, an intake, something. Prototype out those subsystems inside of your code. How they work doesn't matter. And you can build actions using this framework for using those manipulators. All that stuff can be done way ahead of time. Now, all of the autonomous drive-based stuff, we already know our drivetrain is going to be a 6-wheel drop center, so we can easily implement all of the path following stuff, right? The only thing that we will have to do is update the image on our web interface that we use to generate our paths so that we know where we're going. All of the code exists to generate and follow the paths. All of the code exists to follow our autonomous modes. All of the code exists to run our subsystems. The only thing we have left to implement is what actually happens inside the subsystem. The drive base, we can use the exact same code as last year, maybe a couple updates and improvements. Maybe we want to add shifting, right, with different transmissions, add a shifter in. In our code from last year, there's already a shifter that's been prototyped out. All you have to do is uncomment it and instantiate it, and now it shifts. Things, right? Maybe you want to add vision in. Well, we already have vision completed from 2017, so we'll take that vision and just dump it in the robot. That's good to go. We try to get everything done as far before the season starts as we can, and we never do. You know, we're always continually working on it. Yes, question.
Last you said I had to have the reading something a while ago. It was like about what you can and can't use going in.
As long as you publish everything, you can use anything you want, software-wise. Mechanical people don't have that same nicety, you know? They have to make all, like, you can't have prefab stuff that you've made going into the next season. But software, as long as you've published it, you can use it, because everyone can use it. That being said, there are some people out there who don't publish their code and use it anyways, and those guys, bad. But
not great.
it's not, but it's not enforced either, right? So it's like, who's really to blame here? But at the same time, yes, we will be publishing everything that we're developing now going into next year. Good luck figuring out how to use it, because there is no documentation. The stuff that we provide for you guys to actually use is well documented. But if you want to use our stuff pre-season, there won't be any documentation. When we release it at the end of our season, we'll try and put as much documentation as we can.
You with, 2017 going in, there was some library maintenance. So all of our 2017 code ended up being obsolete by the time, and that programmer graduated. So you think that's starting to happen?
So that's a good question. So the way we deal with that is that every device that we use inside of our code that's like a third-party library, like the NavX, like the Talon SRX, those kinds of things, we create drivers for them, right? And that being just a Java wrapper that contains all of the methods that we use in our source code are wrapped with our own class. So we only use our own class everywhere throughout the rest of our program. Then, if Crossroad Electronics updates their library, then all we have to do is update our wrapper driver file so that it's compatible with all the rest of our code. Because we assume that we're able to do all the same things that we used to be able to do next year, even if they're called different things. So that way, we rewrite the driver wrapper to provide all the same functionality using our own methods, just updated with their new library changes. That way, it's independent of anything. So the other things that we do with that is sometimes we make drivers polymorphic. Like this year on our robot, our LEDs have a Morse code translator built into them, so they can output Morse code messages and flash and stuff when things go wrong. So it also does indicative like error code messages that are displayed through Morse code, like when comm is lost, they'll say SOS and stuff like that. And what we do with that is originally we started with a PWM digital I/O driver from the Rio that used like RGB drivers for the LEDs. So we wrote an LED driver that was polymorphic, and then we can supplement that driver using either the PWM channels from the Robo Rio, or what we ended up using later on, which was the device from Crossroad Electronics called the Canifier, which has a PWM output over CAN bus. But the rest of our code doesn't change, only the instantiation of what driver we load. Any other questions? All right. Well, thank you guys very much for coming today. I appreciate it.
You guys did really well this year, so shout out to you for that.
Thank you. What team are you guys on?
1922. We did not do so well this year, so yeah.
No, I know.
Yeah.
But you guys are doing a lot of very interesting things.
Yeah. We're doing a lot better this off season. We were finalists at Governor's Cup and River Raid.